Good morning. This is Calculus in the AM, in case you're just joining us in the PM. I'm your host, Mr. Schnelke. We're actually recording this in the afternoon, coming to you live this afternoon for Calculus in the AM. So people are watching in another time zone. Anyways, this is continuity, page 78. In our textbook, 2.3 is the section. But don't worry about the textbook right now. Now, I think you guys have an intuitive grasp of what continuity means. Continuous. Function's continuous, no breaks. Smooth. Smooth. Okay. Now, in general, polynomial functions are continuous. You don't even have to, like if you're just given the equation, polynomial, no rational part to it, right? It's going to be continuous. There's 4 types of discontinuities, and they tend to appear then with rational functions or piecewise functions, sometimes absolute value functions, which can always be translated into a piecewise function. Okay, let's take a look at this. Infinite discontinuities, vertical asymptote lines. I put this as a reminder. You know, you can't divide by 0, so you are going to have a discontinuity if some x value gives you a 0 on the denominator. Now here's the example for x over x minus 2. Discontinuous at 2. Now, this is just nothing to do on this example. It's notes, like so you're aware. Infinite discontinuity. Does it make sense why it's called infinite? It goes up forever or it goes down forever. Infinite discontinuities could be, if you had a square involved, pardon me, infinite discontinuities could be 2 things both going to positive infinity, right? But left and right. Okay, still considered infinite. Jump discontinuities, mostly found in piecewise functions, like this little guy here. If I graph that, is not included. This value is included, but you notice there's a jump. So the word jump makes sense, right? That's classified as a jump discontinuity. And that's at 2 as well. X equals 2 is where. I'm giving the domain location, right? Where it happens. A removable discontinuity then. Removable discontinuities occur when there's a hole, but you're going to call them removables in the graph due to an indeterminate part of the function. Indeterminate, what is that again? That's the word, and this is why if you want to jot it down, indeterminate, 0 out of 0. That's that form. With the original expression the way it was given, when you try to evaluate the limit, is it 0 out of 0? We'll take a look here. If I said limit of x approaching 2 for this function, put it in, it's 4 minus 4 on the numerator, 2 minus 2 on the, that's 0 out of 0. You have to be talking about the original expression, because of course, if you were evaluating the limit as x approaches 2 for this, you would factor that and you would cancel out, and you could evaluate the limit. But that's removable, okay? And that exists, again, I gave one at 2. Removables. By the way, here's another type of removable. So for this one, if I created a piecewise function, and I had, you know, maybe I said for the piecewise function, you know, curly brackets here, for all real numbers except x equals 2, and I could indicate that a number of ways with interval notation or greater than, less than, or even just the words all reals, comma, x equals naught, like can't equal 2. Anyways, that's what I would say for this. And then at 2, my second criteria might have been then equals, okay, I put it 2, I don't want to be confusing here. 1 when x equals 2. I could do that too. That's still removable, right? Because it looks like I have this graph and I've removed something from it, literally, right? And created that hole. So that's also removable. But I'll erase that. But that makes sense that it's still a removable type if you see the picture of the graph. You don't come across oscillating discontinuity much. But the word oscillate means up and down, right? If you try to graph this, don't. It'll take your calculator a little while. But if you do, what happens is, what is the problem here? 1 over 0 is what you can see that as sine of 1 over x approaches 0, it just gets, it's just a big blah. It's a mess. Anyways, and it doesn't cross. You can't evaluate at 0. Okay? So that's why we call that an oscillating. Has no limit as it approaches 0. And there you go, 4 types. We're mainly going to come across the 3 types: infinite, jump, and remove. Now, test for continuity at a point. I'm going to do some flipping back and forth. And I'm going to tell you that this comes up enough that I wouldn't say you have to memorize it on purpose, but you're going to do it enough that if you don't have it memorized within the next week or so, you'll have trouble. You'll have it memorized in May or April. When is the test? It's in May. Yeah, so in May. You should have it memorized. So if you want, if you're that type of person, memorize, maybe. Now, it doesn't make sense right now to memorize without understanding. So we're going to memorize eventually. But first, let's understand it. That's what I'm working on. Test for continuity at a point. A function, f of x, whatever. That could be x squared plus 5 divided, it goes on. It's continuous at the point x equals b. So b is a value like 3 or 2 or negative 17. It's continuous at this point x equals b if all of the following conditions are satisfied. Think of this as a 1, 2, 3 ABC test. The minute one fails, and go in this order, don't move on. Just say not continuous since. Okay, we'll talk about this. First thing is that no calculus involved with this. Does the function exist when you plug the number in to the original function? Is it a real number that you get out of that value? Okay? Now, I'll show you what I mean by that first A, and then we'll work through something here. But, right here, does the function exist at 2? The way this number 3? No, it doesn't. So, no question, not continuous. If I gave that piecewise function I was making up earlier, though, it does exist at 2. X equals 2, right? So I'd have to move on to the next step. Now, the second thing is, and we'll get practice, I'm just talking this through, but you really pay attention. So you don't just look at the examples, don't try to jot anything down as I do. B, the second test is as x approaches that number, so like x approaching 2 for the function. Can you get an answer for that limit? Remember, you're approaching from left and right. So if I come back to this one, and I'm using this example where I put this dot in, we know right now the way it was given, we would have stopped. But does the limit exist? Yeah. From the left and the right, I definitely come to it and then evaluate it actually for that. And in this case, you'd evaluate it as 4, right? So this is 4, this is 1, the y value is the function. Okay. I think you can see where this is going then. If A and B pass, check, check. Does the limit give you the same answer as just the function without calculus, just the way you would have? If it does, it's continuous. If it doesn't, it's not continuous. So going back to my example that I made up, just to visually look at, the way here you can see 2 different answers. 4 and 1 aren't the same, so the limit's not equal. You'd say, you would have went through A and B and said, check, yep, check, and then C, the limit does not give you the same value as the function at B. However, if this was the case, you see how everything gives you 4, whether it's the limit or, then that's continuous. You filled in the hole. Oh. Now, I flipped the page on purpose. We'll look at continuity principles afterwards. Which condition, so flip the page to 4. I just wanted everything on a page rule was. And we'll look through question A. Which condition for the test of continuity at a point is not satisfied at x equals -1? So, for A, the first test, now since we have A, B, C here, I'm going to use 1, 2, 3, little Roman numerals. The first thing I test is, does f of -1 exist? And that's your first test. Does it? No. Okay, so, doesn't exist. I stop then. Or undefined. You could, actually that's a more concise one word. F -1 of -1 is undefined, not continuous. For me, CTS is fine for continuous. On an AP evaluation, like as in the big test, use the full spelling of the word, because I don't know that they know it's CTS. It's not a standard abbreviation. The next one, so B. I start with B here. First thing I test, at -1. Do I have an answer? You're darn tootin'. This is sort of like the one I was making up before, right? When x equals -1, just give it a 2. Don't think about it. Check. I move along. So it exists at f of -1. Then does the limit exist? From the left, from the right? So basically, I've got to try to evaluate this. X approaching -1 for g of x thing. X squared plus 5x plus 4 this is the portion that I would use, right? For either side. And this means I can do it all at once. So, can you factor that? Oh, yeah. 4 plus 1, right? Gives me 5. So yeah, I can do this. Oh, I'm going to do it on the get too cramped. When I'm at x approaching -1, x plus 4, x plus 1, x plus 1. And I think you can see where this goes. We've got a canceled factor. Divide out of the top and the bottom. -1 plus 4 is 3. So the limit in this scenario is 3. So we've got to move to the third test. This was not planned. So, out the front door. Welcome back after our brief intermission. We had a chance to get snacks from the lobby. Third test is, does the limit give you the same value as the function? Here's how you say it doesn't. Is, just go like this. Now, f of -1, does it equal the limit of x approaching -1? Now, don't rewrite the function. Just put it as f of x. But it doesn't. Therefore, not continuous, right?
It should be equal to 3.
Just a second. Now, I've forgotten my numbers because of that unplanned fire drill. Because 2 is not 3, right? Yeah. That's where we were. So don't use the actual numbers. State it like that. Oh.
Where did we get 3? Oh, never mind. Thanks.
Yeah, I know. We're all off like, where were we 5, 6, 7 minutes ago? Yeah.
Where did we get 2 from? Outside.
What's that?
Where is the 2 from?
Okay, the 2 is from the function when you just use -1. I know. It's really disruptive. Anyways. So are we good with this? We've been through all 3 tests. Let's just take a look here. By the way, if it was continuous, if I asked you, is this continuous? If not, state why. if it was continuous, so if this said 3 right here, as that, and I came out with a 3 here, I would just put this equal sign and wouldn't cross it out, and I'd say, therefore, it is continuous at x equals -1, right? If that was the case. Now, C. I'll switch colors because we might blend into this. Testing at -1. So, does h of -1 exist? Yep, the category I use is the x is less than or equal to -1 category, so I just put that in there. 1 minus -3 is -2, but it's absolute value, so we just got 2. And then, or what did I say? -1. Sorry, I was using +1. Blah, blah, blah. Look at this. For this category, we use this, -1 minus 3. Sorry, I use 1 minus 3. So it's equal to 4. Anyways. And I'll look for this. The first test works. I'm trying to hurry and I didn't put my first test kind of thing here. A, B, C, or whatever. I'm only using 1s, 2s, 3s because these are labeled A, B, C already. So my second test is, does the limit exist? Now this time, I'm going to have to test the limit from the left and the right separately. Why? Because the limit for the left side and the right side use 2 different parts of the function, right? The other one here, I could do this at one step because to the left of -1, to the right of -1, it used the same equation portion, right? Now the piece, and the piecewise function that I use on the left, would be this one. So when I'm doing this, here we go. Limit of x approaching -1 from the left, I've got to choose the absolute value portion. Now, is this making some sense? Why I chose that category? Okay. Now, you just solve this one. There's nothing wrong with subbing it. We did already. It's 4, right? Okay, so the left-sided limit works. Does the right-sided limit work? The limit x approaching -1, but from the right-hand side, we use this portion of the equation, 2x plus 11. Put it in brackets so you know that it's all included there. And basically you sub in -1, and you got -2 plus 11, that's 9, right? So do the left and the right side limits match? No. So that means the limit of x approaching -1, both sides, for the function h of x is undefined. Therefore, not continuous at x equals -1. This is only testing at one particular x value in the domain, possible domain. Yes?
How did -1 work for the first one? Because it's
Sure.
equals 4, but isn't x less than or greater or equal to -1?
Okay, here, right?
Yeah.
You're talking about this. Yeah. But it's the limit. If I drew this, right, I would just have this value, right, coming from the left, it would just come to that anyways, right? Okay. Actually, it would be going up, but anyways. But regardless, like on the picture. Yeah. That helps you. On the other side, it would be a jump discontinuity, actually. So that's that portion. I'm just now looking and revising with what kind of time we have here. I suppose, yeah, we'll have some, let me see here, because that just slowed us down even doing those examples here. Yeah, we could take a couple days. We'll have a work class tomorrow. Okay, back to this. Continuity principles. all constant functions are continuous. Does that make sense? What's a constant function example? I see your hand going like that, but a polynomial is not a constant function. Well, no, there's one specific. X equals 5, or y equals 5 is a constant function. It's equal to a number, a constant number, and throughout its whole domain, it's the same value. So example, f of x equals 17, or negative 12, or whatever. That's just a horizontal line. So there's no breaks in it, right? It's called constant because whether x equals negative 5 or positive 1 million, it's still 17. Right? The following types of functions are continuous at every point in their domain, but this is really important. I'll just underline it in non-disappearing name. Okay, continuous within the x values in their domain. Polynomials, yep, and that's x squared, etc. Rationals, now you might be saying, but I know what rationals are. Most examples of non-continuous functions that you had before were rationals. Come back to that. Power functions. Oh, I'll just undo this. That's just x to the 4. Roots, okay, square root of x, square root of x minus 2, cube root, etc. Trig functions in their domain. I could think of some that aren't continuous, but it's the word in their domain, and I'll show you with a rational. Exponential functions, logarithmic functions. Now you might even be thinking like logarithmic functions. Where does a logarithmic function's domain start even? What can you not put it? Or you guys are more familiar, this is the same question. If I said the root of x, so I say f of x equals square root of x. This is an easy one. It's a sideways parabola, but it's only half of it, right? To graph. What is its domain? Equal to or greater? Yeah. Yep. So the domain is x such that it's greater than or equal to 0. Once you start at 0, though, everything is continuous, right? Now, with a rational function, you might be thinking, what? So if I say g of x, I guess my arrow's over there. I'll take the easiest one, 1 over x. But you're going to say, I know this, and you know this graph, right? Horizontal and vertical asymptotes at 0, the axes. But what's the domain restriction? It can't equal 0. So 0 isn't in the domain. It's continuous everywhere else in, right? So in its domain. Do you guys understand now why
Like
say
if
that?
there's a piecewise function, and you'd say x can equal to -1, and there's x equal to 1.
Well, if it depends how the piecewise function is constructed, so it won't, and it'll be constructed probably of these kind of types of functions. Okay? Later on with trig functions, you'll see there's gaps in the tangent function and stuff like that too, but domains.
So that statement's just like, it depends on the type of function, just to think their domain.
Yeah. So within their domain, like I say, that these aren't guaranteed to be continuous at all real numbers, because not all real numbers are in their domain necessarily. Okay? And then finally, if f and g are continuous functions, so are, if you do some operations on these, if you add the two functions together, the result will be continuous. If you subtract the two functions, so if I had, x squared is my one function, that's continuous. X cubed is my other function, so if I took x cubed minus x squared, I'm guaranteed that's continuous. If you multiply the two functions, you'll get a continuous, and if you divide so long as you're not dividing by a value that will give you 0. We know that's always. The other thing too is, and I added this in, that was from the Thiessen textbook that I've referenced before. The composite functions of continuous functions are continuous. So, in this particular example, f of g of x would be continuous. If you put a continuous function inside another continuous function. So what? You're thinking, well, guess what? This one. Find and classify discontinuities, if any, for each of the following functions. So, sometimes this is where it helps if you can just kind of visualize a function's graph without graphing it, it helps. But let's just see here. Can you tell where are we going to have a problem, first of all? At 2. Okay, we got a 0. But then you right away look, is it, if I put 2 in there, I'd have 2 over 0. So it's not like it's indeterminate. Kind of discontinuity happens when you have like 5 divided by 0 or something like that. 1 divided. What did we have? Because we looked at limits before. And if you can't remember, you can't remember. Pardon? They're infinite. Those, remember, if you take a number divided by 0, like as you approach that number, as you approach 2, you'll get an infinite discontinuity happen. Okay, so this is infinite. Categorize. If you want to just say disk for me, and you tell me the type and at the value, x equals 2. So we know the problem spot in D, I'm sure. Now I'm going to factor this one because you guys don't know your cubes. No, I think it is. Okay. If I take this one, I'll switch pen colors. Remember, a few years ago, 5 years ago, it was made illegal to factor cubes, something like that. They took it out of the curriculum. Anyways, you're going to get x plus 1, x squared minus x plus 1. It's been so long since I taught it now that I forget and stuff. Anyways, I can tell you that that second quadratic portion won't factor any further. But what it does is it gets rid of this problem spot. Now, I'm not going to leave it crossed out. It's going to disappear. But -1 is the problem spot. But when you can remove the spot from an indeterminate form, what do we call that?
Hole.
It's a hole, yeah.
Discontinuity.
So, it's a hole is what it looks like, but what's the proper name then? A removable. It's like a chunk has been removed from your graph. It is a hole. So we're going to say removable discontinuity. So if you can remove the factor that was giving you grief, for example, literally, that's what it is. Okay? Now this one, the C. I'll do C on the right-hand side, then I'll do D on the left. So I'll switch colors again, C. You're thinking, ugh. 5 is going to be the trouble spot. If I put 5 in there, I get 0 out of 0, right? Test it always, because if it was a number out of 0, then you know it's infinite, right? So then I got a factor inside this. And I'm thinking here.
X plus 1 is
Now, because I'm doing stuff on here and I'm just loosely doing this stuff, I'm not using limit notation, but I'm going to have to think this way. So here's what I'm going to do for my next step. I'm going to write in the limit notation. We're approaching 5, right? From the left or from the right. So I'm going to just go limit of x approaching 5, because we know that's the trouble spot that we're wondering about. I can see that it's going to be removed. Right? Now, here's what I'm wondering. I'm just going to rewrite this, and I know it seems silly, but I should have done this in the first place. Put the limit notation in. Now, just because I'm really only, I know somehow I can get this out of there, right? let's think this through. Maybe I'm going to add something to this. From the left and from the right. So I'm going to do this from the left. You see my little minus sign that I've just put in there? Approaching 5 from the left. So an example of 5 from the left is 4.9999. Okay. In that neighborhood. If I only focus on this part, because I know it'll cancel, but if you put 4.9 in there, let's think the easy part. 4.9 minus 5 is negative, right? Let's say this is negative as well, but because it's in absolute value, it'll be positive. So when you factor that out, because this will also be positive, right? Just incidentally, but don't worry about that. I guess I should. When you factor this portion out, what should you be taking out? This cancels with this, but it's leaving behind a 1 or a negative 1? Okay, so negative 1. And then we've got the other chunk here. How did I show that last year? Yeah, that's a good way to do it, though. So, this is going to be equal to, I'm evaluating right now. I've crossed this out in my mind here. I'm just saying negative 1 on the first portion, and then 5 plus 4. Does that make sense? You gotta, there's a lot of, the arithmetic isn't hard, it's a lot of conceptual kind of stuff. Okay. Then, the limit, let me change colors again, just so that we know it's not the other limit of x approaching 5 from the right-hand side. Now, with this one, if you put in 5.1, for example, you get positive over positive. It works, doesn't it? It's positive 1, and then 5. It's positive 9 is what comes out of this. You guys get the idea? It's the reverse. Not 100% that everybody does.
It's 9.
Yeah. I'm going to emphasize that it's 9. It's positive 9. Just so you really see that the limit doesn't exist here. What happens then at 5, if you were graphing this, it would jump from negative 9 to positive 9 when you're graphing. So it's a jump discontinuity at 5. Yes?
There's confusion how 1 is 9, 1 is negative 9.
Sure, I'll slow down then. I'll just write this down first of all. Therefore, and then we'll come back to this. Because yeah, I got the sense that some people got it and some. Okay. Tell you what. Let's see here. I'm just going to only just take a look at this. And do you notice? Because often people think, oh, piecewise is probably a jump. But you know what? What did it say here? Find and classify discontinuity. There's a chance it actually equals 3. There's a discontinuity, eh? Or does it say anything? Because if you test it at 2, anyways, there's an infinite discontinuity at 3, and you could test that one at 2. I'm not going to do that one because I think it's more important that we come up with this here. How did this work here? Because there's a few ways of thinking about this. Now, I'm just saying this is thinking step. You don't have to rewrite this. But this step here, the limit, I'm going to just do this here, and I'm just going to think this through. X minus 5, I'm just rewriting it over here. Because I know the doll's going to rewrite it. Now, you can kind of see, I think I can cancel this out, right? But just literally think, if I use something to the left, so 4.9, I'm going to put this in here. And then you can use this argument at 4.999 and 4.999, you know what I mean. So this is what I'm doing. absolute value. So this is what you're thinking. If I use a number smaller than 5, but really close to 5, do you see that this bracket comes out as a negative? This comes out as a positive, guaranteed. And this is why I'm saying very close. If you chose 4, okay, if it was x minus 4, we'd agree. We wouldn't anyways. Okay. But keep it close when you're thinking this through. You say, well, this would be a negative and a positive. And this would be a negative. But this is what I'm thinking here. Negative value, positive number. I don't really care what the numbers are, right? I'm just trying to come up, first of all, with what this is, and positive. That's sort of how I'm thinking of these.
Negative positive.
Right. However, because this is negative and it's in absolute values, this value will be the same, like negative 0.1, right? This is negative 0.1. But they will cancel each other, right? But this numerator value would have been changed in sign. Do you follow me on that? Because it's in the absolute values.
So it would be changed to positive.
That would be changed to positive, and you'd be dividing by negative. So that's where this comes from.
I understand the first one, but the second one I was positive.
Oh, the second one that's positive. Now think through with 5.1. The same kind of argument here. I'm just going to get rid of this jazz here. Yeah?
Is number D?
Okay, delete first. I'm just going to finish this. Now if you use 5.1, you'd have positive, positive. So they're going to just cancel out and be positive 1.
Oh, one's going from the left eye.
And then 5, because 5.1 plugged in there. Okay, yeah. And this would be 9. Now I'm going to stop the recording. And I knew that.